going through. I gotta turn this music down a little. Yeah. All right, that's good. Okay, and we're looking good. All right, hello everyone. Welcome back to OpenGL. It is our 53rd episode. It's pretty fucking good. It's a lot of shit. Well, today we're gonna be. It's gonna be a pretty straightforward episode, or maybe not too straightforward, but it'll be a very climactic episode per se, because we're going to be taking the collision algorithms that we've been working on for the past few maybe 10 episodes. No, it's not, it hasn't been 10, but the custom collision meshes that we've been working on recently, and we're going to be integrating them with the Octree so that we can get some accurate collision detection, which is going to be pretty cool. So yeah, we're going to be determining when to use collision meshes in the actual detection, when not to, when to use coarse grain or coarse checking, when to use fine grain checking, and we will determine all that as we walk through this. So I will just pull the code up, and we're going to be dividing this up into three small chunks. The first part is going to be we want to standardize the bounding region as a sphere for our models. And the reason why is because I believe I've talked about this before, but when we have a bounding region as a rectangle, as an axis-aligned bounding box, that doesn't allow for rotations. However, with the sphere, no matter where you rotate it, it will always have, it will always contain the model or the collision mesh, whichever one you want. So we got to standardize that so that all models are going to use the sphere, so that we can have some rotations. So we'll start in model.h here, and we're just going to remove the ability to customize this. So where we have the bounding type, the bound types attribute, just delete that. Don't need that anymore. And then also in the parameter list for the model constructor, just delete the bound types parameter there, just because we don't want to allow it to be changed. And then in model.cpp, we're going to do the same thing. So just remove the bound types from the parameter list, and then also remove the initialization from the initialization list there. Now you should be getting a few errors here because in our process mesh, we initialize a bounding region with a bound type, which is not an attribute anymore. So when we set up our bounding region in the process mesh function, we need to pass in a what do we want to pass in? We want to pass in just a sphere as a default type. So bound types sphere. So we're always creating a bounding region using a sphere, and as a result, when we go ahead and process the minimum and maximum, we don't have to have this if statement here to determine if we would only want the min and max, or if we wanted to do the sphere calculations. So what we can do is, let me just pull this up real quick. Where is it? Come on. Here it is. Is this right? Where am I right now? Oh, okay. Here we are. Yeah. So we can remove this if statement here, because we don't want to assign anything for a rectangular, the axis-aligned bounding box region, and we only want to process the sphere. So the first step here is to calculate the max distance from the center. So we have a center, which is just determined as the average of the minimum and the maximum values. Then we have our original center, set the, and then also here, what we want to do is, or wait, does that come after? Yes, that comes after. Give me 2 seconds, I just need to write this down. Okay. So we set the original center, then we have our placeholder for the maximum radius squared. Then we go through the for loop, radius squared. We just add the distance and determine if we have a new maximum, and then we set the radius as the square root of the maximum, which is stuff that we've seen so far. All right. And everything else is the same there. All right, and then since we removed the bounding sphere from the parameter list, or the bound type from the parameter list, this influences all the inherited models here. So we have to go through each of these models here and change the parameter list. So we can start in sphere and gun, because we only need to remove the bound types from the parameter, the superconstructor parameter list. So sphere and gun, it's the only change there, because these are model files, so the model class itself will calculate the sphere automatically in this method here. However, with cube and plane, we have to do this ourselves. So remove the bound types from the superclass constructor list, constructor parameter list, and then when we go down and set up our bounding region, we cannot have it as an axis line bounding box anymore. We need to create a sphere. Oops. Yeah. So we're going to have a bounding region, BR, and we're going to initialize it with a center of 0. And then the radius is just going to be the distance from the center to any corner of the box. And the reason why is because that's just the maximum distance you will get in a cube. So if you do the distance formula and then you do all that, you will get that. Oops, hold on a second. You will get that the radius should be the square root of 3 divided by 2. Make sure you have your floats in there. Alright, so that's that for the cube. And then in plane, it's going to be something very similar. We're going to have the bounding region, BR as a center width of 0, and then the max distance will just be the distance to one of the corners, which is going to be 1 divided by the square root of 2.0. If you use the distance formula, and the distance is just 0, so it's going to be the square root of 0.5 squared plus 0.5 squared, which gets you 1 over the square root of 2. What's up, Inez? I hope I pronounced that right. So yeah, just maximum distance to any of the corners, and that's the stuff there. And then there's going to be times when we don't know what the maximum distance is, where we can't customize this. So when we have a custom, if we had a more custom, say a more custom mesh, a more custom collision mesh, and we didn't know what the maximum distance would be, we want to add the same type of loop here that we use to calculate the maximum distance into the collision mesh class. So we can go ahead and hop into collisionmesh.cpp, and we have to include limits like that. And then we're going to go to the constructor of the collision mesh, where we process all the points here, and the way that we're going to do this is going to be it's going to be the same type of algorithm. It's just going to be a little different in terms of how we approach this. So let me actually look at this real quick. So we're gonna have the same minimum and maximum. So GLM vec3 min, it's gonna be equal to, or we're gonna initialize all the components with standard numeric limits float infinity. And the reason why we're doing infinity, positive infinity for the minimum, is because everything will be less than that. So we're getting the first point that we process, we're going to find a smaller value as the first minimum. And then similarly for max, we're going to have standard numeric limits. Float is negative infinity a thing? I don't think so. So what we can just do is just say max is equal to negative 1.0 float times min, because this will be negative infinity, which is going to be, so everything will be larger than that, which is exactly what we want. Alright, now we're going to have in the points list, we get the coordinates from the array that we pass in here, and then we want to go through each of the coordinates and determine if it's smaller or larger than the min or the maximum. So we're going to have a for loop here. So for int I is equal to 0, I is less than 3, I plus plus. And if points at I, or this should not be I, the inner loop should be j. So if points at I at j is less than min, min at j, then we found a new minimum. So this, we're just going to set it. So min at j is going to be equal to points at I at j. And then on the other hand, we're going to say if points at I at j is greater than max at j, then we found a new maximum. So max at j is going to be equal to points at I at j. Alright, simple enough. And then, as before, we're going to calculate the center as the average. So glm vec3 center is going to be equal to, in parentheses, min plus max divided by 2.0 float. Just the average there. And then we're going to do the same max radius squared, all that jazz. So we'll have float max radius squared is equal to 0.0 float. Then for unsigned int I is equal to 0, I is less than number of points, I plus plus. Then we're going to calculate the radius squared for the ith point, so radius squared is equal to 0.0. For int j is equal to 0, j is less than 3, j plus plus. We're just going to go through each of the components. So radius squared plus equals, in parentheses, points at I at j minus center at j, and then we're just going to multiply it by itself. So points times points at I at j times minus center at j. So just getting the distance to the center. And then if radius squared is greater than max radius squared, then we're just going to, we found a new maximum radius. So max radius squared is going to be equal to radius squared, just like so. And then we'll set the radius. So we'll have this dot br is equal to bounding region. The center is going to be the center, and the radius will be the square root of the max radius squared. Like that. And then we have to set the collision mesh in the, or wait, sorry, that doesn't exist yet. Let's get too ahead of myself there. Alright, so that's the first part. We standardized the sphere, so everything will now be, all the bounding regions will be calculated as a sphere for the models. The Octree cells will still remain as boxes. Alright, next part is to link the bounding region and the collision mesh. The reason why is because in our Octree, where is it? The Octree, here it is. In our Octree, trying to find a collision. Here we go, check collisions. We have bounding regions as the objects in the cells. and we're going to keep it that way. We're not going to, it would be very expensive just to store a bunch of faces, especially if you have a bunch of faces, even with the reduced amount in collision faces. And that would also require us to store lists of transformed faces, which would just be very complex, very it would be a lot of memory that we don't want to use, especially if we have a large amount of instances. There's no need, or it's just a complete waste to do that. So we're going to want to link the two without having to go through the model the model tree. So in our bounding region class, we have a pointer to an instance, and the instance has a string representing the model ID, or the instance ID, which will then point to a model. However, we would have to go, let me just make sure. So the rigid body has a model ID and an instance ID. So if we wanted to get either the model or the instance to get access to the collision mesh, what we would have to do is go through the model tree or the instance trie, which would require us to pass in parameters from the scene class, which is very complicated. However, it could just be simpler to attach a pointer to a collision mesh to each bounding region. And then it would just allow us to say br.collisionmesh.faces at I or whatever .test collision with this other face, something like that. So we're going to essentially just attach the two in a certain way. So we'll start in model.cpp, and after when we're calculating the bounding region center or the bounding region sphere, we just want to say I completely forgot. We have to go into bounds.h first because we actually don't have it added yet. So in bounds.h, we have to have a forward declaration here for the collision mesh. So class collision mesh. And this is just a forward declaration, so we don't have any circular definitions or circular includes. So just that. And then in the bounding region, we're going to have a pointer to the collision mesh. So collision mesh pointer, collision mesh. And then in bounds.cpp, we want to include the collision mesh file. So this entails include ./physics/collisionmesh.h. So now we have a definition for this class here. And we can do this, we don't have to have the declaration in the header file over here because we just have a pointer, and all pointers have a constant size, and it's just some pointer to an unspecified area of memory. So we don't really care what's there or what that memory represents. We just want the pointer to the memory. And then we're giving the definition to that pointer in here so that we can access the attributes accordingly. All right, now in model.cpp, we want to first set this this to null beforehand. So when we're calculating our bounding region sphere in our process mesh, we're assuming that we don't have a custom collision mesh for now because we're loading this in from a file. However, we may add that at some point to load a custom collision mesh in from a file, which I do want to look at actually. However, for now, we're just going to say that br.collisionmesh is equal to null when we're calculating this sphere over here. And then in collisionmesh.cpp, when we say, let me just figure this out, okay. When we set the when we initialize or construct the bounding region, what we want to attach to it is just say this.br.collisionmesh is equal to this. So they have a circular pointer, so they point to each other. so that the collision mesh can get quick access to a bounding region, send it to the model, and also the Octree can get access to the collision mesh from the bounding region, which is inside of each Octree node. So we now have circular pointers, which is pretty cool. All right, last part of the stream today. We've been going along pretty quickly. We're actually going to look in the Octree now. So we're only going to be working in check collisions self. Alright, so what I want to do is I want to delete everything inside the second if statement. So we have the for loop going through each bounding region in the objects list, and then we have our course check over here, and then I'm just going to delete that right there. So course check for bounding region intersection. Alright, so course check has been passed. So in the for loop, we go through each bounding region. If the bounding region intersects with the object's bounding region, so if the two spheres intersect, we know that the course check has passed. So now we have three possible. In the beginning of each iteration of the for loop, we have four possibilities. They can either both have a collision mesh. They can neither of them have a collision mesh, and then one has a collision mesh and the other doesn't, or the other has a collision mesh and the first one does not. So we're going to have four different possibilities here. And it's going to be pretty symmetrical. So we will start by saying, if in the if statement here in each iteration, we're going to have a nested if statement. So if br.collision mesh. So this means that BR has a collision mesh. So we want to test against all the faces in BR to determine if we have an accurate collision. So we're going to first get the unsigned integer of number of faces BR, which is equal to br.collision mesh dot faces dot size. Just like that. And then if object.collision mesh, then we know that they both have collision meshes. So we have to determine the intersection of each of the faces. So this is going to be an n squared operation, and I do know that sucks because it's each iteration of the main loop, and there could be multiple objects in the node, so it could become messy. So we're just gonna leave it as n squared for now, but then we will, in the next videos, we'll add some priority checking. We'll add some optimizations that don't require us to do this check every single time. So we're gonna say we have to check all faces in BR against all faces in OBJ. So we're gonna have Boolean. We're just gonna have an outer Boolean. So Boolean collision found is equal to true or false. Then for int I is equal to 0, or sorry, we have to have an integer out here first. Unsigned integer number faces object is equal to object.collision mesh.faces dot size, just so we can get that there too. So for int I is equal to 0, I is less than number of faces BR and not collision found. I plus plus. And then for int j is equal to 0, j is less than number of faces object this time, j plus plus. And then we want to determine the collision of the faces. So if br.collision mesh dot faces at I, so the ith face in BR dot collides with face, and the parameters that we're going to pass into this function are going to be br.instance. So br.instance is the instance of the face that we're calling here. So br.collisionMesh, so we want to pass in br's instance. Then the face we want to test collision for is object.collisionMesh.faces at j. And then the object's bounding region is the third parameter, so obj.instance. So if this returns true, we have a collision. So I'm going to have a print statement here, so standard cout case 1. I'm just going to label it just so we know exactly what we see, just to make sure it's all correct. So instance instance br.instance.instance ID, and I'm just going to have the type here. This is just similar to the print statement that we had before, and if you don't really need to look at this or care about this, but I'm just doing it just so we can get a visual indicator of when it happens. And then just collides with. Object.instance.instance ID. And then I'm just going to print out the object instance model ID. Just like that. And then we're going to set collision found to true. And then break. Or we actually don't need the collision found right now, but we will just do a break, because we don't want to test any more collisions for the current face of BR, since we already found one collision. Alright, so that's when they both have collision meshes. Now, in the if statement, if br.collisionMesh, we're going to have an else here. So this means that BR has a collision mesh, object does not. So check all faces in BR against the object's sphere. So for int I is equal to 0, I is less than number of faces BR, I++. Then we're going to have a similar if statement, but this time we're going to be calling on collides with sphere. So if br.collisionMesh.points or .faces at I .collides with sphere, pass in the instance will be br.instance, and the sphere to collide with is obj. If that returns true, we're going to have this. I'm going to have the same print statement, except I'm going to have it say case 2 this time. And then we will break after as well. Alright, so that concludes if BR has a collision mesh. Now otherwise, BR does not have a collision mesh. So we want to have the same two if nested if statements. So if obj.collisionMesh, then object has a collision mesh, BR does not. So check all faces in obj against BR's sphere. So it's going to be the same type of if statement here, but we're going to get an unsigned integer first. So unsigned integer number of faces object is equal to object.collisionMesh.faces.size. And then for int I is equal to 0, I is less than number of faces object, I++. And then in this loop, we're going to have the same if statement. So if object.collisionMesh.faces at I collides with sphere, and the parameters we're going to pass in, object.instance is this instance, and the bounding region will be BR. If that returns true, we're going to have the same print statement, except it's going to be case 3 this time. Alright, now else. Neither of them have a collision mesh, but the coarse grain test passed. And we know that because that's just this larger if statement up here, if BR intersects with the object. That's testing the intersection of both of these spheres. So therefore, we already know that the bounding regions already intersect. Test collision between the spheres, and we already know that passed. So we will just print out that this happened, and we will print out a case 4 here. All right, yeah. So those are the 4 cases there. I actually want to try something here. Let's try creating or having the integers outside of the if statements. So unsigned integer number of faces BR is equal to br.collision mesh, and if that exists, we're going to have br.collision mesh dot faces dot size. Otherwise, set it to 0. And then the same thing for the object. Unsigned integer number of faces obj is equal to the same thing. What's up, Yusuf? You're on episode 10. That's good. Yeah, there's a long way to go, but it ramps up pretty quickly. But thank you for the kind words. Yeah. So number of faces object is going to be the same thing. So object dot collision mesh question mark object.collision mesh dot faces dot size, otherwise 0. And then we can just test these integers in the if statements. So if br.collision mesh becomes if number of faces br, and then if object.collision mesh, that both times that happens just becomes if number of faces object. Because if there's 0, then we know that there is no collision mesh to be checked, so therefore we will just rely on the coarse grain check. All right, yeah, that looks about it, or that looks like about it. I know for a fact that there are a few gimmicks that I need to work out, but this is the general algorithm that we're going to be following from now on. There's a few Octree errors. There was indexing things that I need to debug, and I will definitely look at that. But this video is about just integrating this stuff. I don't care about the errors. I just want to see that it works for the most part. So if we run this now, we should get something. I also re-enabled the spheres, so when we press F, the spheres will be launched. So here we go. So if I launch a sphere, we have a case 3, which, is that right? Bunch of case 3s and a case 2, okay. Alright, so case 3 was that the object has a collision mesh and the bounding region does not. Okay, but it was still right. So let me go into main.cpp and I'm going to crank down the size a bit on the sphere. So I'll make this 0.1 or something just so we can see it a little better. And I'll just leave the energy the same. Where are we? Here we are. There's this. Oops, I don't know what's going on. There we go. Okay, so it's giving it. So case 3 is what we're getting. Did I just fuck up this spelling or something here? Okay, I think I fucked up the spelling. Hold on. Oh, there we go. Alright, that should look a little better. But I did think there were... I didn't think that looked entirely right. I'm going to be honest with you. Okay, maybe... Fuck. Oh, I think I know what it is. Oh, okay. Okay, so we were seeing that the sphere was colliding with itself, which is not what we wanted. So, in the beginning of each of the bounding region iterations, I forgot to do this, but we have to make sure that the instance IDs are not the same. So if br.instance ID does not equal object.instance, or I'll just say if they are equal, object.instance ID, then continue. So we don't want to test collisions between the same mesh. Or with the same instance. Alright, this should look a little better. Okay. And we're getting a lamp collides with a sphere, case 2, which means that they're moving over here, so case 2. So BR has a collision mesh, but object does not. So object is the moving object, which is the sphere, and we do not have a collision mesh there, which is correct. And the lamp, which is the object we're testing against, has a collision mesh, which we programmed, which is correct. So fuck yeah. Alright, let me also re-enable the boxes so that we can render those. Okay, let's run this just so we can see the boxes and all. What's happening? There we go. Alright, boxes, there we go. That looks about right. Because no matter how we rotate it, we're going to get it inside the sphere, sorry. So we have a little bit of space on the outside, but it's really a sphere. So let me just move this over a bit. Like so. Alright, so we have a collision there, no collision, no collision, no collision, even though it's going through the sphere. Because it's definitely going through the sphere, but look at that, there's no collision, which is perfect. Absolutely nutty right there. And we get the plane collision, and oh, is this actually working? Oh wait, this is fucking sick. Oh my god, because this is what I was talking about. There were bugs with this. I don't know why it wasn't working, but it wasn't working with the plane on my when I was testing this. This is fucking sick. So that means that there's no errors with our collision detection. Oh, that's fucking sick. Oh, that's awesome. That is all. You know, this is actually fucking sick. Holy crap. Okay, this is awesome. Okay, wow. Holy crap. This is holy shit. Oh, wow, that's fucking cool. Oh, man. Oh, fuck yeah, that's great. Oh, this is sick. Oh, my god. Oh, this is amazing. Oh, fuck yes. Ooh, man, wow. Okay, this is good. Okay, fuck that. I don't really care. I'll figure that out later. That does not have to do with the collision algorithm, which we know works. We just proved it works. And we're good. So there's indexing errors that I said that we have to work out. Octree errors we got to work out. Don't know what, but we will work them out. The point is that we did this. However, I think we know what this calls for. I have this bookmarked. I don't know if any of you guys remember this, but in the first or in the last Octree video that we did, I played this video. So let's just play this real quick. Let me actually turn the volume up. Hold on a second. Where are we? Desktop audio. Let's crank this up a bit. Here we go. This is such a bad video. I should not be. I'm at risk here to watch this. Yeah, so that's me right about now. But fuck yeah, okay, it works. That's good. Oh man, good shit. Honestly, good shit. Ooh, wow. Okay, yeah, you can play around with that. But anyway, yeah, that's all I have for you guys today. This was cool. Hope you guys enjoyed. Hope you learned something. I don't know, maybe you learned something. But yeah, this is good. So we are on the way to making a very accurate collision system that will be generalizable soon when we start adding or start creating our own more complex collision meshes that extend beyond a cube or a plane. Maybe even we could do it with the gun or something. I have no clue how I would do that, but maybe that's coming down the pipe. But yeah, anyway, I hope you guys enjoyed. This is cool. I'm excited. I am elated right now. I can't even express how much happy hormone I'm getting right now. Yeah, alright, I hope you guys enjoyed, and I'll see you guys next time. Have a good one.